All right. All right. Welcome, everybody. Today I get to introduce myself. We've all heard the introduction that Melinda gave 2 weeks ago when we had the first installment of this pair of seminars. In the first installment, if you remember, I introduced Birtracks notation for permutations and for states in QCD that are globally possible. And today's talk speaks of an application. This was a talk that I originally gave at a workshop on Birtracks that was showcasing techniques, Birtracks techniques, and applications thereof. And these are actually quite broad in atomic physics. In all manner of fields, you find applications of this. Birtracks help visualize certain expressions and in this particular case, in wave functions, in states, in color signals that play an enormous role in QCD because, well, there are no colored states in QCD. All macroscopic objects are color neutral. Color is the charge of the strong interaction. And so states that establish that all our particles that appear in a particular event are in the color neutral states are of utmost importance. What I'm going to talk about today has a long history. There are contributions from all manner of students and colleagues in this. You see the long list here on the slide. So this is roughly the outline of the talk. I will start off with the application that got me into this, and that is geomorphic evolution and the color glass condensate. So this is a case in which we're dealing with a scattering event at extremely high energies. The energies are so extreme that, in fact, the particles that scatter only interact with modes that are much softer than the scattering objects, and essentially the only thing that can happen is that the hard particles are going to flip the orientation of the color vector. They cannot be deflected during the scattering event, so the only thing that happens is really that the colors get rotated, and that is what the Wilson lines are talking about. Wilson lines are group elements. Group elements in this case that will depend on some transverse position that summarize the amount of color rotation that happens during the scattering. So that is what the Wilson lines are talking about. And what the evolution equation refers to is the statement that the amount of rotation depends on the energy at which this is happening, and therefore the QCD averages of a correlator of several Wilson lines will actually change with the energy at which the scattering is. The evolution equation for this is the geomorphic equation that predicts what the energy dependence of these correlators is. Right? That's the point. The problem is that these equations actually are not just one equation or two or three that you need to solve simultaneously. This actually becomes an infinite set of coupled equations. The infinite sets of equations are really hard to solve, right? And so usually what one does in order to get around this is one finds approximation schemes to truncate the set, to make that set finite. And of course, if you want to do something like this in QCD, there are well-known sets of infinite coupled equations, the sets of Weigert equations for QCD, for example. And those are enormously hard to truncate in a way that does not break gauge invariance. Gauge invariance gets in the way of just chopping off these equations after the nth equation. Right? So these equations, those twin equations, start off with an equation for field expectation values, then for propagators, and then for 3-point functions and for 4-point functions. But the notion of n-point function in QCD is not a gauge invariant concept. So truncating these equations is really hard. But here we actually stand a chance of doing of simplifying our infinite set of equations to a finite set of equations in a way that is gauge invariant. And you have to be quite clever, and Birtracks help you write down the expressions in a meaningful way. And then I'll just give you a bit of a sneak peek on where we want to use this, how far we are, and where we want to use this. Okay, so this is the goal today. All right, let's go into this. So this is the briefest introduction to GIMWOP that I could manage, that I hope is still digestible. So what we're doing here is deep inelastic scattering. And please look at the diagram at the right bottom corner. And I'm drawing my diagrams the way you would write down expressions in a formula. So read them from right to left. On the right is a state that comes in. That state contains a wiggly line that you see at the top that splits into two lines. The wiggly line is the photon that comes in. So I'm scattering an electron, and that electron interacts with a target, say a proton or nucleus. This is the thing at the bottom that you see in this diagram. This is the black line converting into this gray blob. That's the target. So in order to interact at very high energies, this photon has to split into a QQ bar pair. So this is the lines that you see on top. And then comes a blue vertical line. That blue vertical line symbolizes the gluon field that the target creates, that the QQ bar pair on the top encounters, that it moves through, and that induces a rotation of the color vectors. So that is what you see. This big red, this thick blue bar, and the red arrows indicate there is some non-trivial rotation of the color vector going in this diagram. The variables that you see attached to this are interesting. There are transverse positions x and y. This happens because this interaction is essentially instantaneous. How does that come about? This comes about at very high energy, and what you see there on the left is a variable y, also expressed as log 1 over x. This is Birtracks. Essentially, what you see, this variable is the log of the total energy in this collision divided by the transverse by the transverse momentum in the collision. So that is what you see. That is the variable that is big. Humongous energy compared to the momentum transfer that has happened in the collision. That is a situation in which your projectile is strongly boosted against the target. Right? That means if you look at a Minkowski diagram, as on the left, there are two diagrams. That it's a longitudinal direction horizontally, and the vertical direction is time. Right? And now remember what a boost is doing. A boost squishes one light cone direction, and it stretches the other. This is the diagram on the left bottom. This is a boosted version of a coordinate grid that is shown in the diagram on top. Right? So an extreme boost, therefore, squeezes any function that has an extent, in this case, an x minus, in the extreme limit in the intradelta distribution. It just happens at one value of x minus, and it erases all dependence on x plus, because the x plus, right, any oscillations in the x plus direction, any variations in the x plus direction are stretched out over an infinite interval in the extreme case. So in the extreme case, you end up with a gluon field that is written. So this is also sketched with the support in these blue boxes. This is it's shown, right? I have a modulated gluon field, then I boost it, and then something happens to it. It becomes constant in one direction and absolutely, Lorentz contracted in the other direction. And you see a formula for the gluon field. So the gluon field has a delta distribution X minus dependence, no X plus dependence, and only transverse fields in it. That is why the Wilson lines that I pick up, the color rotations, only know about the transverse place, the transverse order, place where they punch through that gluon field.
But we don't want to waste too much time, but I want to know why such a seemingly physical statement is expressed through something that is gauge dependent like that.
Well, okay, so this looks a little bit like it is just a gluon field. I can also talk about the gluon field strength. So then I'm talking about the plus. There is one big component in there, which is still not gauge invariant. It's on gauge covariant, not as badly gauge dependent as this. But then I can look at Lorentz scalars, and you see that this thing drives the largest contribution. So this thing being a gluon field, so something like this happens in all gauges, no matter which gauge you choose, with the exception of one gauge, a gauge where you make this big component, which is the plus component here, right? The one component is also enhanced by the boost factor, and all the other components are suppressed. There's only one gauge in which this is not true, and that is a gauge where you maliciously set this one component to 0. Now, that doesn't mean that the contributions go away. It just means that you hide them in other components and in the contributions that are moved out to infinity. So this is the unfortunate gauge in which these calculations become infinitely harder, because you have to pick up contributions out of infinity. Very, very hard. In all other gauges, this is the thing that drives it. So this is, and you can, by gauge transforming this, you can track where these contributions go, but it's not worth the bother. It just, the description in terms of gluon fields changes. The physics result remains the same. All right. So now let me take these things and try to get to a cross section. I'm already using pictures that are very close, diagrams that are very close to Birtracks, and we'll get even closer to standard Birtracks in a moment. In order to get a cross section, what I've just written, the diagram that you've just seen me introduce, is one where I pick up a complete color rotation. Okay? So this is a group element, and group elements always, you can write, in SU3, you can always write them as an exponential. So if you look at this exponential, there's a term that contains no gluon field. So exponentials of the gluon field, so the first term in this exponential series contains no gluon. That is a contribution in which nothing changes. So, or to say this in an equivalent physics language is that what I've written down is an S matrix element. In order to get to a cross section, I need to pick out the piece where something changes, right? The T matrix, in other words, if this is a familiar item. So in order to get to the cross section, I need to subtract out the thing where there is no blue bar, no strong gluon field in it. So that is the piece that contributes to scattering, and therefore to a scattering cross section. Right? Things where the contribution where something has changed in the final state compared to the. And now I calculate the cross section, and this is the sigma total that is written down there for gamma star scattering on A, and the A stands for a nucleus with A nucleons in it. And I have, right, the thing that I wrote minus the thing where nothing happens squared up. That gives me the cross section. Now let me factorize this and make it a little more Birtrack in the next step. I just multiply this out and I factor out the wave functions to the left and to the right of my square brackets. So there's a wave function on the right of the virtual photon as it splits into its contribution where it splits into a QQ bar. At the bottom, there's a color neutral wave function of the proton, and there's the complex conjugate on the other side. Right? This is a kettling, this is a proton. And in the middle is the thing that makes the cross section. It comes from multiplying out these functions. There are two contributions where we have presence of a gluon field multiplying something that has no gluon, right? No interacting gluon field in it. Those are the last two contributions. There's one obvious contribution where I have nothing times nothing. That goes into the into the term that has a 2 in front. And then there is a term where I have gluon field on both sides. That is a little funny because we're integrating over all momenta in the final states. And what that integral does is it identifies the positions of the Wilson lines in the amplitude and the complex conjugate amplitude. And since we are talking about unitary elements, right? Unitary group elements, I have a U dagger at X times a U at X, and they go away. And the term where the term where I have blue times blue is actually the same as the term that has nothing times nothing. That makes the factor of 2. Okay, so that's the factor of 2. Now, if you read this out loud, you notice, okay, there are these wave functions. They actually just make a bunch of Bessel functions. The color part of this induces a trace over Wilson lines. And in fact, it produces the real part because you see twice the real part, because what you see there is twice the real part of something that contains the product of 2 Wilson. Okay, so this is the expression that we're dealing with at leading order. Now, of course, something like this won't stand, right? In GCD, you know it's a quantum field theory, and once you have a state where there's a QQ bar and you let it go for a little while, it will start emitting gluons. No way to avoid this. These gluons, however, are, if we are in the perturbative domain, suppressed by a factor. These gluon emissions are suppressed by a factor of things. So if the kinematics are right, I can do a perturbative expansion, right? And keep adding gluons. And what this transparency is telling you is you can summarize this emission of a gluon and the associated virtual corrections that go with it by a single operation that you have to iterate. You get an equation that tells you, okay, as I change my energy, I allow more and more phase space for these additional gluons to appear in the final state. And I can parametrize this or describe this through an operator that is actually a Hermitian operator that is known as the Junor point. This is totally regular, and obviously, an equation like this you can nominally solve through exponentiating that operator. That operator, so what is in there? So this operator acts in the picture before, it acts on contributions that have 2 Wilson lines in it, and it actually hits the things that have the Wilson lines. It doesn't change stuff that don't have Wilson lines. So it actually turns out that in this situation where I've started with just 2 Wilson lines, right? 2 Wilson lines on these blue bars. Or I can actually start with arbitrarily many Wilson lines. I've simplified my annotation now a little bit. I've left off the blue bars, but the red arrows are still the Wilson lines. And it turns out that if I take an arbitrary product of Wilson lines and complex conjugate Wilson lines represent quarks going through the field and scattering. U dagger represents an anti-quark going through this field and scattering. Then I can still describe this correlator and its average through that same operator. So this is just going through a compilation of Feynman diagrams, and that is what pops out. You need to work a little to see that it doesn't matter how many you have, but the idea is relatively clear. This is a leading order calculation, and I can emit and reabsorb one gluon, right? So what I can never connect more than two particles, hot particles in the game by such a line. And therefore, in the end, it doesn't matter how many I have. What I get is just the sum of contributions where I connect any possible pair. Yeah, and this operator is written in a way or designed in a way that it actually does this. And if I write my average through a weight, I can actually turn this into an equation for the weight. So one equation, right, for the change that governs the energy dependence of any Wilson line correlator in this situation. And the Wilson line correlator defines the cross section, right? So that is one thing you want. This is enormously elegant, but this is a functional equation. And if you solve it, assuming you can, you sum all corrections that carry a single log of energy times an alpha S. So this is a typical thing that you do when you go for a normalization. Yeah.
First, this is the equation about the dipole. That was what you have when you had deep elastic scattering in mind.
Yeah. Is this relevant to anything?
Yeah.
You will see a little later. Yes, it's even relevant for deep elastic scattering because those other guys actually also show up if I try to solve the equation. I cannot get rid of them. Okay. So what am I doing when I solve this equation, right? So I picked out in order to get this Tumor Hamiltonian, I picked out the contributions that carry the large logarithm of this energy that I claim to be big, right? So if I look at all the diagrams that carry this log are enhanced, right? So I would like to reorder perturbation theory in a way that I gather together all contributions where this large log compensates the smallness of the coupling. Coupling is small, right? This is the assumption. Coupling is small, but the log is large. But if I try now to write down all possible Feynman diagrams that contribute to this thing at any possible order, there will be diagrams that are not small just because they have a coupling constant in front. But if there are enough powers of the log, as many powers of the log as of alpha, if this log is large enough, it can make this contribution this prefactor of order 1. So I would like to grab all those out of this infinite tower, right? This infinite set of parameters. And this equation does that if you solve it. Right? There are suppressed contributions. The next order in this thing would be things that have 1 alpha S more than powers of the log. And you go further down to inaccuracy and higher up inaccuracy by having more excess alpha S. So you have to reorganize perturbation theory totally, and this equation does that for leading order at this point. Okay. So if you can solve this, you get the energy dependence. Now, what is this operator? Well, here comes another mathematical conundrum into the game. This is a functional differential operator. You see these nubblers that carry a color index A here or B and the coordinates X and Y. These are functional derivatives that you can express in terms of these Wilson line fields that carry that transverse coordinate at which your hot particles punch through this gluon field. This is just functional derivatives of certain sorts. And if you look at them, what they do is, in effect, they plonk a generator of the Lie algebra right next to each U factor they find, up to some signs that are adjusted so that something interesting. If you know enough differential geometry, then then these operators actually generate the left and right invariant vector fields on SUN. The left and right invariant vector fields actually lead to the geodesics on the Lie group. So there's a lot of geometry and a lot of in the background that you don't need to know if you want to do the predominant calculation, but that helps illustrate what is actually going on. So this is actually what this operator does. It moves these Wilson lines around in geodesic directions and reshuffles the values of these Wilson lines in a way that connects different positions, because these operate on have different arguments associated with them. There's some integral kernel that is perfectly harmless, that comes out directly of the QCD calculation. And the interesting thing is this is connected with left and right invariant vector fields, because these objects actually these derivatives conform to the commutation relations of SUN, but only if the two transverse coordinates are the same, because you talk about two different groups. If you talk about gauge symmetries, if you talk about this position versus that position. So these guys only don't commute if they talk about the same particle. In essence, that is what is happening in the last line down here. And the left and right invariants always commute with each other. So this is just sort of differential geometry updated for field theory.
How indices are these objects?
Yeah.
What do they run from?
They are just the adjoint color indices. There's nothing else going on. This is just talking about Gluon vertices. What this does is inserts the generator that comes with the three Gluon vertex onto the Wilson. So they're just joint generators. So from 1 through NC squared minus 1. And I keep NC generic here because it helps, right? So with those, I can write down a formal solution to this equation that doesn't buy me much, other than knowing, okay, this can be solved, right? It has a solution. Okay. Right. So now let's look at the dipoles that we looked at, because that was the physics example that started. If I write this out, apply this operator, this is the expression I get for the thing that actually changes, and that is the correlator of the two Wilson. So the average of a y, right? And there's trace ux times u diagram. And you see on the right-hand side, there is a term, this is the very last term, that just has the same thing in it. But the first term in the round brackets has an additional Wilson line at a point z. That is actually the adjoint representation. That's what the tilde is for. And therefore, there are adjoint indices on the thing. That represents the newly produced gluon also scattering off the target and also getting its color. Now, these expressions, if you look at them, you see there is no color index free, right? The fundamental indices are eaten up by the traces, and the adjoint indices A and B are eaten up on generators. They're contracted onto generators. So there are just color singlets everywhere in this step. Now let me draw this in Birtracks, in the hope that it gets a little clearer what is going on. So on the left, the Birtrack for the U dagger U is that closed thing. You see a state, a quark singlet state on the right, as in how we discussed quark singlet state last time around. It's just a Kronecker delta. And there's a Kronecker delta on the other side that actually makes up the trace for the U and U dagger. Same thing in the last term. The middle term contains two Wilson lines, one for quark, one for antiquark. This is symbolized by the direction of the red arrows. And then there is the gluon Wilson line going on, connected with a dotted line. And you see states that I've also drawn last time around. We'll get them. You'll get to see them again in a moment. I'll flash this once more what you've seen last time. So you have a state here maybe I can try and use my pointer. Right, this is the state of to the right of where I'm of the line I'm drawing. This is a color singlet state of a QQ bar with the glue on, and its complex conjugate is on the other side. And you get, if you take a Birtrack, you get its conjugate by flipping it over and reversing the direction of the arrow, and that's precisely what you see me do for the state that for the final state that this is going into. Well, what you see here clearly is an equation for something that has two Wilson lines in it, correlator of two Wilson lines, and on the right hand side there's a correlator that has three Wilson, for the antiport and the additional dual. So this is not a closed equation. Yeah, right. So you need an equation for the thing that has three Wilson lines in it, because it feeds the equation that I want to solve. Unfortunately, that turns into an infinite hierarchy. If you look at the equation for the thing with three Wilson lines, you find contributions with 4. The ones with 4 are fed by something that has 5. Doesn't terminate at all. So that's uncomfortable, right? At leading order, there are numerical ways of getting around this using a Fokker-Blunt description of this. I'm not going to talk about this here, but that trick doesn't work if we go to NLO. This is a leading order description because, yeah, talking about NLO at this point, it's largely pointless. So at NLO, the tricks we had for leading order won't work. We have to do something else. And this is the truncating that I just talked about in the introduction. Right? We need to do something to take this infinite set of coupled equations, pare it down into a finite set. So how would you do this? Well, you might think, okay, now this is a little bit desperate, right? I'm trying to do something here that is violating the structure. If you do this in a clever way, it's actually going to be informative. But it's very clear that from the outset, in order for this to be informative and useful, you have to be careful to maintain the constraints on this. And one that is very, very obvious is that that must come from gauge invariance. The obvious thing is, imagine you take the target away. Okay? So now all Wilson lines become trivial, they become 1. It's actually gauge invariant to having all Wilson lines being the same. But the nice thing is just set them all to 1. And if you look at this, you see that in this equation, if you set them all to 1, the terms are normalized such that you actually get out 1 for all terms, on the right hand side, 2 terms cancel. So nothing happens as you hope, right? As you require for a physically relevant equation. And this actually, if you look at this carefully, this imposes all manner of constraints on the evolution equation itself. Okay. So how do you try and pare this infinite set down to something finite in an intelligent manner? There are a couple of rules, and you get hints about these rules if you look at the correlators that floated about in the equation itself. Right? You see me write down things that contain a U and a U dagger, a U and a dagger in a joint, and I write down all possible options here, and they're all connected in coincidence limits where I take one or more of these coordinates to be the same. If the coordinates become the same, right, the Wilson lines become the same. And certain things must then reduce and simplify, because if you multiply U with a U dagger, it's gone, right? So this is happening in this, and so this looks exceedingly complicated if you write it out with U's and U daggers. You get lengthy expressions. The top right shows what is behind this in Birtracks. If you take the thing in the middle that has the U and the U dagger and the gluon in it, if you take the U and the U dagger on top of each other, that contribution starts to look like a gluon, and you get the diagram on the right hand side, two gluon Wilson. If you take the gluon on top of either the quark or the antiquark, you also get a simplification. This thing is indistinguishable of a correlator of a quark and an antiquark. The gluon, if it's right on top, can't be resolved. You can't see it. The color algebra bears this out. It's actually quite interesting that this actually happens. Yes.
The two one on the right hand side, like, and it's something the same thing, the arrows are pointing to me.
That doesn't matter. The direction. I could draw it the other way around, but it doesn't matter. Yeah, probably should have drawn together. You're right. I should have drawn. Okay. So, what is this? This is actually something that happens in more general patterns. If I look at the equations that I would get in this hierarchy. And this is something I've shown you previously in the last talk. I made states for 3 Q-bar pairs that are color singlets. I wrote them out as Birtracks, and I made them, if you remember, just by taking all permutations of 3 objects and directly mapping them onto each of, well, the first 4 states. The last 2 are anti-symmetrized and symmetrized versions, respectively, of the 2 states that I would get better. They're nicely orthogonal, and although I have not done it on this slide because it gets too lengthy, whenever you do something like this, you should better go and normalize the states to unity. They are nicely orthogonal. As written, they are not normalized. And now I can look at these states and stick 3 Q-bar pairs in, right? U daggers in between, and that is written sort of as a matrix of, right, color singlet objects that can go into correlators on the left. You see on the diagonal, this is state into itself, and the other ones are transition elements from one colorless state into one of the other colorless states. Okay, so this is the game that we have here. And now interesting things happen if I take coincidence lengths. If I take, say, what have I done? I have done, yeah, in the first step, I have done the top quark at the same position as the top antiquark. And if you now pick out one of those, let's say this one here, I claim I get a 0. The 0 comes about because I should draw this a little bigger. Let me draw this. What I'm getting is I have the top end of this diagram, right, had a generator going out. There was something else down here. And what? Let me just reproduce the picture. Yeah, and I had something like here, Wilson lines everywhere. If this is a U, this is a U dagger. If the position is the same, and this here means there's a generator inserted, and this means this is the indices are closed up. So this means that there's a U multiplying a U dagger at the same spot. That makes a 1. But now there's a generator, and what I'm ending up is I look at the trace of a generator, and that is 0. So all the zeros that you see there are made by simply having the trace of a generator appearing. That kills all the contributions. The last box does one more coincidence of it. That takes the next Q-bar pair and takes a local limit. And you see diagrams appearing that you already had seen in the original equation that I wrote down. If you look at this thing here, for example, this is just the QQ bar correlator because these things are just numbers. These are just factors of NC. This is the QQ bar blue correlator just drawn upside down, right? And there are more complicated ones down here. Now, if you look at the Jim-Walk equation, what it does to correlators of 3 QQ bars, you see that those 4 on top are actually, if I look at the Jim-Walk equation of those 4, and in the left-hand corner of the middle thing, they're on the right-hand side, all the other guys in the bottom right-hand corner appear as the driving diagrams for the evolution. Right? So now you see that if I go broad, throw many QQ bar pairs in, I actually look at more complicated evolution equations that would come down further down the line in these hierarchies, right? And moreover, if I take these coincidence limits, I get the simpler equations back out. So the more complicated equations know about the simpler equations as limits where these points become the same. So there's a lot of regularity in these equations that are not totally obvious when you look at it from naively. So this is, so yeah, right. So here I pick out the top left corner again, 2 QQ bar pairs. I take one coincidence limit and I see, now I have the ingredients of my original simple equation that I wrote down previously in the thing. And if I take one further limit, nothing's left. Right? So now I want to go and find a way to store the information in these correlators in a way that allows me to truncate the equations. Okay. Assume I'm able to solve the Jim-Walk equation in general. What I will then get, of course, and I know that these things contribute to my cross-section in some way. Then I know, okay, this is a matrix space. So as a function of energy or y, this traces out a trajectory in this function space, right? It's a matrix space. So, okay, it will have tangents. And I can ask for those tangents, right? And I can ask how the tangent vectors change as I change energy. So the equation that you just saw has a formal solution in terms of a matrix exponential. It's essentially a flow equation, but in matrix form. Flow of differential equation, here expressed as a matrix. I read this, so I read this matrix space as a vector space, so I can express how this point changes as I move it, right? As it moves through the vector space. So imagine I just find a basis for the matrix space, right? Then I have vector components, 4 vector components. And in this 4-dimensional space, this vector moves. Right? And that's that movement I follow using this thing. And of course, so this operator here, right, falls into some 1 parameter group. Can break this 1 parameter group, means I can break this up in bits and pieces and glue it together. Small pieces of evolution going on, of change going on, and that nicely becomes a C group. But its exponent, so this is a curved thing, right? Its tangents live in some vector space, and that's easier to graph. So I'm going to go to find those exponents, or parametrize them. And now I need a couple of rules to do so, because I don't want to introduce things into my parameterization that don't gel with Jim-Walk, right? That they break some rule that Jim-Walk imposes on us, and I don't want this to be too restrictive. So then I cannot pick up everything that Jim wants to do. So I want something that is as general as possible, but just constrained enough not to make a mistake. Okay, so the rules that you collect if you stare at this, that your parameterization must obey is that, okay, Wilson line correlators as I change energy must become Wilson line correlators. Again, that means all these coincidences must work. Gauge invariance must work. Rule number 2, this came out of Robert Moorman's MSc, is that these matrices actually are symmetric. So if I find a basis for my metric space, I better choose a basis that separates out symmetric matrices from antisymmetric matrices, because then my evolution operator becomes block diagonal. Right? I nicely separate this out, and I've removed everything automatically that would talk about crosstalk. So this helps with the economy of doing this. Rule number 3 is again gauge invariance. I need to be able to do color rotations globally on the singlet states that come in and the single states that come out, and I need to be able to do this independently of each other with different color, arbitrary global color rotations, because Jim walk behaves that way. So my parameterization should do the same. The other thing is the cross section should remain real. That is a little more subtle. That I won't be able to clarify in this talk very well. So how do we achieve this? Well, we write down a monster ansatz for this n. That we design so that it does everything that it's supposed to do. So the simplest thing that I can write is, and I write this in terms of endpoint functions. The idea is to inject endpoint functions in a particular way that are able to record endpoint correlations through endpoint correlations between these Wilson lines, but do it in a way that all the rules are satisfied. So the simplest thing I can do is throw in 2-point functions. This is the sort of the second line of this. Right? So I must do this in a way that I'm not taking color in or out. So I need to insert Gluon vertices in a way into these diagrams where the color that goes in is taken out of it. The only thing that I can do if I put 2 Gluon vertices in there is a conical delta in the adjoint domain. That's the only thing I can write. I can do this using left invariant, right invariant objects. What I cannot do at the 2-point level is mix a left invariant derivative with a right invariant derivative, because that would force the right global color rotation to be the same as the left color rotation. That is one rule that comes in at the 2-point functions. And then I can go on and add more of them, right? Contemplating having arbitrarily many. Well, more than 4 is ridiculous for any practical. Okay. Nobody will measure anything more detailed than a 4-point correlation. Okay. Forget about it. But this is the generic thing that you can write down. What we do here is I'm using this left and right invariant vector fields and coincidence constraints on G to satisfy rule 1. Rule 1 was all coincidence limits work. The symmetry between, I write down expressions that are symmetric between the left and the right invariant vector fields in order to ensure that the parameterization doesn't mix symmetric parts of the matrix with antisymmetric parts. So that's another thing. And again, gauge invariance, left independent of right. This is that mixed terms with left invariant and right invariant derivatives in it must have color structures that factorize. One for the left, one for the right. Rule 4 in this case says for the total cross section, there are no 3-point correlators. That's more of a calculation, just announcing this. No explanation. So how should you think about these? Well, these endpoint functions, you should think about them as the equivalent of structure functions. But now for Wilson. Right? We will get one for each independent gluon, linearly independent orthogonal color singlet states for gluons. So these CA1 to AN, we can derive by writing down color singlet state for gluons. The techniques that I've shown you before with Birtracks apply seriously to this. This was work of Jonathan Rayner to n = 4 that we have done explicitly. If you go through all of this, what you end up with is that your Wilson-like correlators are now parametrized by these genes, right? Through this exponential E. You can probably only do this for anything beyond the 3-point function numerically, but that doesn't matter. It gives you something parametrized by these objects. You can then measure these objects. It's gauge invariant, no matter where you truncate this hierarchy, which end or endpoint correlations you say stop. And in that limit, with this constraint, I don't have to do any other limits, such as the large NC limit. So you can solve these equations in the large NC limit because everything factorizes in the large NC limit in a very simplistic manner. But the large NC limit is something we want to go beyond, right? People want to calculate cross sections at the LHC at next to leading order accuracy. And 1/NC corrections come with a 1/9 prefactor, right? They're only suppressed with a 1/9. So this competes against the accuracy that you gain, or destroys the accuracy that you gain by going to higher order interpolation. Right, so let me show you what happens for the simple equation if I just use the 2-point. Because there I can actually solve all the ingredients for all the ingredients in terms of those endpoints. Right?
This equation you have over here.
Yeah.
Top note.
Yeah.
This is only for 2-point function, but we have that curve.
Well, I calculate something for the 2-point function that contains the 3-point function, right?
Yeah.
But now I'm telling you in my parametrization, I get an expression for both of these objects in terms of the same 2-point function, in terms of the same G, right? The one for the QQ-bar correlator is just an exponential in G. The one for the QQ-bar blue is a more complicated exponential in linear combinations of G. But it only contains this 2-point function G. In the large NC limit, if you look at the scaffold, it actually reduces to the large NC limit result that people have been working with in a very nice way. But this is NC exact. This has NC suppressed contributions in the exponent that it has with some example. All the coincidence limits work. There's just enough degrees of freedom to solve one equation, which becomes an equation for G, right? And I can't satisfy any other equation because it's already determined by the first one. But I can't calculate all the other correlators in terms of this G. So this is a 2-point truncation. Now I can in principle go more complicated, but now right, I get a solution in terms of initial conditions for this G at some y0, right? Because I'm solving a differential equation. So what goes still? There's freedom in specifying the initial condition. This is where, in this situation, the non-productive in the initial condition. Just like in the Biglav equation, right? In all those evolution equations, non-productive stuff always sits in the initial condition. That you have to match up to experiments. But once you have it, you have a prediction for more complicated stuff as you move away, right? QCD predicts the change and gives you a long lever arm, possibly adjust the initial condition. Learn about what it looks like. So this is what is going on here. Let's talk a little bit about what we're working on currently, and that is, well, how the heck do we get these gluon singlet states that are hiding in here? And those we get in by just writing this type of answer. So I'm writing just a particular relatively simple situation, endpoint function, endpoint color singlet for gluons, n derivatives of one sort. This is simplified notation. This means there are n such derivatives with all manner of indices and coordinates. Since there's an integral in this thing, I can always commute my integration variable, right? Just renaming stuff. So I can throw in a sum of all these permutations and then rewrite the structure. And what comes out is that, oh, the combination of color structure and endpoint function must be symmetric under simultaneous exchange of color index, gluon color index with coordinate simultaneous swaps. That you can rewrite this with a little theory in terms of operators that you saw as Hermitian projection and transition operators. So this is the example where I have 3 points floating around here. These are projection operators for 3 objects. They become the objects that I can use to sort through my color states. The color states themselves I obtain from, what the heck, where did I have it? Let me go back here. I obtain from this little trick. I just select all the things all the contributions. There are actually 9 of them that do not have a single Q-bar pair. Those go. And I chop off those lines. Then I have a two-gluon state expressed through a trace. I do this everywhere, and I have spanning set for my gluon states. And I use my operators that I had written down here to classify them in totally symmetric, totally antisymmetric, and some mixed symmetry. That is a way of obtaining these and then getting a handle on the features of these endpoints. So that's what we're doing right now. We're working through this. There's quite a bit going on here in terms of symmetry groups of these projection operators. They're invariant subgroups, cosets, lots of math games, quite entertaining. Where this applies, and this is my last slide, where this applies is all situations where I get Wilson lines in the game. So this is in Jungwall, and also surprisingly, maybe in a totally different, right? This is a scattering situation. These Wilson lines also appear in jet production cross section. There it may be visually plausible because you have these hot particles that shoot out. And if you don't have a magnetic field, they shoot out straight. Those are Wilson lines that you pick up. Essentially, they are color rotated by the soft gluons that you don't see in the front. And there some of the game with the coincidence limits actually announces itself differently. There was a long story that I remember when people started talking about jet events at colliders. This was at Lab. Fermilab did a lot of jet physics Rick there were doing, they were just trying to measure, quantify these jet events, right? They noticed they look peculiar, so measure this. What it turned out they did, they defined the observables in a way that they were not, that you couldn't do a perturbative calculation to recover them, to predict them. Turn out this is related to a question of whether your observable, how the way you formulate it is collinear in infrared safe. Collinear safe in the sense that if you take two of these, if you take a 3 jet event and you have a calculational device to get this, and you take 2 of those and you make 2 of those legs align, that this expression reduces to what your algorithm, your procedure produces for a 2 jet event. If that doesn't happen, you get into trouble. This is the equivalent of a coincidence limit in Gmor. 2 Wilson lines align, and therefore, right, something special happens. This is the game. This is the game that you saw at work right there. Infrared safety is a similar thing. You cannot do much. You also need to get the simple thing back. If you emit a gluon that has no energy, that has a zero form, essentially a zero form, this limit must reduce to the thing with 1 less. So all of these can be parameterized with the same tools and the same techniques, and you can make sure that if you have the Wilson lines, they do the right thing. So this applies to infrared safe infrared and collinear safe observables in any of those. So it's very technical, but it is a tool set to extract information from these things in the same sense as structure functions give you information about non-competitive features in the detailed class. Right, thanks. Question.
I have a question, I think it's on like slide 13, you're talking about
Slide 13. Okay, let's see if we can.
location variance.
This. That one.
Yeah. No,
There were a few 13s because
I see. I think the slide is pretty safe, but it's not following where the constraints of gauge where this is coming from. We're putting in this concept with the PSPs and the PCs, but I'm not following where the gauge restriction constraint is coming into those variables.
so right, you have Wilson lines. You have a stack of Wilson lines that talk about a bunch of hard particles moving through something. And we're looking at situations where these hard particles came out of the same color signal. So overall, they must be in a global color signal. Right? Plasma diagrams always do this. If you put in an overall color singlet, what comes out is an overall color singlet. It might be a different overall color singlet. As you see, there are plenty of non-identical color signlets. So if you look at this over here, the state you have is an overall color singlet. So you must be able to rotate this with the same gauge transformation on all legs. Now something happens in the middle, but you're not feeding color into, taking color out. So over here, that state that gobbles it up also must be a color signal, but independently of the thing that I set in. So I must be able to color rotate this overall with the same color rotation on all legs. That's global. That's global color rotation and gauge symmetry that comes in. The coincidence limits are a refinement of it, right? And if I have these states, proper color color singlets and coupled, that refinement essentially comes out of the map in all these colors.
How do you think that?
Maybe we need to draw a couple more diagrams. More questions?
Yeah, kind of based on similar to what Dave was saying. So I understand in Steve, you had some color neutral coming in, like you said, the final state will be color neutral. Is there anything which tells you that it must be more like locally color neutral, or is it just like you have something colorful stuff going in different directions, that would be fine autocorrecting. So it's not forcing you into
This is very, very interesting. I mean, this is actually something I'm working on with Simon Platzer. Simon has given us a while ago, if you remember, and he's one of the guys contributed to it. Right? One of the maintainers, or one of the major monopolists. And we had an interesting observation. So how do these multicolored, they emit particles by sticking in vertices into the calculation with propagators. They do leading contribution, they pick up leading contribution. But the way you emit is then gets a weight, and the weight comes from virtual corrections in a way. And now they found out by analyzing the diagrams that you should not take a naive weight, but you should use a weight that comes from these virtual contributions that knows about all the other, about all the objects you can emit from. And if you look at the configuration of weights that they found, lo and behold, that combination of weights is precisely the combination of G's that you see sitting here. Interesting side observation. So what did improving these weights do? So the multicolors always have a platonic part where you just do the simulating stuff. And then there's a hybridization part, string model or whatnot. The statement is, if you do this following a recipe like this, if you do the hadronic part in a reasonable level, then the effect of the hadronization piece,
your platonic part.
yeah, you do the platonic part having emission weights that have structures like this. So this is a leading order type structure, not an analog structure. So this is just a leading order improvement on the probabilities. But the statement is, if you do it cleverly, the effect of the hadronization part is much, much smaller than if you don't. So there is color correlation in this that knows about distances, because this talks about angles between. So that picks up some of this. Now there is always something that is there in the extreme sort that is absolutely and naturally non-perturbable. Think of two jet units back to back. One colored fork goes this way, one colored fork goes that way. Outcome color neutral happens. So you need to communicate color from one side to the other, or you have nothing that is color neutral. Okay? So from that perspective, this can only be an extremely soft fluid that doesn't manifest. It just fiddles with the Wilson lines. It doesn't manifest. And so that is one of the quirks that we are trying I'm in my head still trying to track. How does that happen? What impact does this have on possible evolution equations that you can write, or on possible observables that you can actually count? This is a statement of how do I characterize an observable in a more advanced version of collinear and infrared safety that might be a little more general than what is in the books at the moment. There are connections between these things. As soon as you have everything in Wilson line, the Wilson lines do it. this is the funny thing. If you can guarantee that you get the interaction of hard with soft parametrized by Wilson lines, you won. Because then all of these features happen because it's just group elements multiplying properly. Yeah. So
Some physics might not be captured.
but some things you might not be able to just capture with these Wilson lines, and that is what we are trying to dig out. So the verdict seems to be, as soon as you have Wilson lines, all of this beauty is happening, and everything's consistent. But if you the issue is the thing you want to measure you're interested in for some reason, is this guaranteed to actually boil down to something like this? Or is there an obstruction? So simple obstructions are clear, but we're after something slightly more. So that's, to me, this is a relatively example because we seem to now have a language and we can actually phrase the question. Any more questions? Not from the youngsters, then what is up?
Yeah, another trivial question. This, what does this equation look like for the three object? So if you have a 3-point.
Now you want to do a proton, right?
Suppose you want.
Yeah, you want to do a proton. So a proton, I have to do it n=3. Right? Our physical protons, I have to do it n=3. At n=4, it would have 4 quarks. Right? Baryons have n quarks in an SU&X theory have n quarks. The way it's there are a couple of exotic ideas of doing it differently by putting the antiquarks in the different representation, but that's that makes life complicated in other ways. And then I can pick up a fixed NC, I can pick it up in an equivalent equation that I can write. I don't have it here, but it's discussed in the papers I wrote with Judy.
What does the kernel look like?
Well, it does contain 3 coordinates, right? Right, 3 external coordinates plus a gluon, right? So it will contain 4, but it will not be very different from this. You will get linear combinations. The emission of 1 is always the same thing.
Doing some effect of PDF loaders.
So now so this is at small Birtracks, right? So in terms of twist expansion that gives you the ordinary PDFs, this is sort of orthogonal. This resums infinitely many twists, but the leading power in X in one of those. So there is an overlap if Q² is extremely large and X is extremely small. Then there is an overlap and there is a connection there where the things become the same or become similar, but then you need to do some both. So that connection is there. There is a really nice paper by Owen Chow that talks about how these things match up, because there are interesting transfer momentum distribution limits in the small x limit that have interesting Wilson line configurations associated with them. Again, Wilson lines pop up in all of these games automatically because of kinematic reasons. But there's always something that is large and that direction that is special. That is not going to be shoved about. And so there are different Wilson line configurations going up into different correlators. That's quite an interesting topic. But it's okay. Another talk or two.
Now going back to the split between the jet physics and the general.
Yeah.
I understand perfectly why, you know, collinear momentum correspond to, this coincidence limit.
Yes.
But this, very low infrared, stuff, what does that correspond to in the visual setting?
It is also just extremely soft guys, but they don't do anything else in Jimbo. Because you cannot rearrange directions. It's because where's the picture? For some reason I seem to have lost the slide. Yeah. For some reason. I had the slide in my last talk. You saw the picture with the light cone and the tangent in my last talk. And so Jim Walk talks about the tangent of the light cone, and there, well, the soft emissions you can rearrange, reshuffle things on the light cone, directions on them. That you can do. In Jim Walk, soft emissions cannot get you off the line. So that's locked. That's one difference. Any more questions? And this is infinite. You can go for hours, you can go for weeks. Pieces. Two, yes. Now, right, I just tried to highlight here where the Birtracks things come in, and I completely lost the physics discussion. This is the process. But, you see, right? If you draw these diagrams, the diagrams themselves have very much guide the eye for what is going on. Whereas the formally that have traces, Wills lines, you don't see what is the incoming state, what is the outgoing state. It's actually just not as obvious which piece of this expression belongs where. And it very much helps to sort through this if you know what is the state that comes in, what is propagating through, and what do I pick up. The diagrams are much easier for the bookkeeping mentally than the explicit expressions that you can write down, can translate them into. That's the point of Birtracks. And that we wouldn't have ever found those without Birtracks. This was Judy Arnott starting as because those are tiny compared to the precursors that, as I've shown you last. Okay. Questions done?
I'm still trying to understand this, this kind of business. So we could write down on the left side of the journal, we could write down some.
So this
was we got 4 quotes.
So where this color comes from is emission from a single line. And it contains a piece of the propagator here, the geometry in which it is going, and what is left is essentially a pi over p dot k. This is the momentum space version of this. And then you Fourier transform this. This is the overall thing, right? Times a generator. That's it, right? Yeah. This P is the momentum that goes here. So momentum P goes in, momentum K goes out here. Momentum of the outgoing. And in the different kinematics, this makes these kernels. So this K that you saw there is essentially made from this dotted into another one on the other side. Yeah. And then you Fourier transform both, and you get a structure like this. So with a little quirk of throwing stuff away that has to do with closing this.
Okay, if I'm staying with what you wrote down, the Gmod stuff, it's for arbitrary endpoint function.
Now this also works if I have 3 cores.
Okay.
in a color singlet state.
or whatever.
Well, NCO, right?
Oh, okay.
Straightforward. Nothing really changes. It is just you can, right? You can emit from more of these guys, so you get combinations of pairings. That's what happens on the right. But you can connect this line with this line. Right? You have those guys. One of them. You can connect this guy to this, to itself, to this guy, to that guy. And you just have to sum over all of these contributions and you get something equally simple. It's just a few more terms.
Yeah, except something with the development, whatever, more coordinates in it.
Right, it's more coordinates on the right hand side, right? Because you have three Wilson lines plus the fourth that is the glue that you throw in.
So, yeah, no, okay, so. Naively, this looks like a peculiarly G-walk thing. But I often hear people talk about a G-walk and BK is somehow equivalent term, but.
Well, BK is the large incident.
But still you can treat arbitrary, arbitrarily many, correlated of arbitrarily many, big,
Well, you do the large and C limit, and the large and C limit factorizes everybody into
the 2.5.
into 2.5. Okay. It's like and it throws away the variance. Right? Large and C makes the variance infinitely heavy, infinitely many quarks in the baryon, which means it completely counts. So that you cannot do.
Yeah, okay, so BK is, you get out 2.8 because there's nothing else into it.
Yeah. But in large and C limit, there are no.
So these are only equivalent to the large and single.
Yeah. One is the large and C limit here. This is general. And it's a trivial large and C limit only if you do these parameterizations. Otherwise, you have to throw in a few more extra words. It's a large and C limit combined with an independent scattering approach, which says two-point functions. Right? So people talk about this in different ways and pay attention to different little difficulties in the semantics or not. So you end up with people who hear what is meant and people who hear what they hear, which might not be what is meant. So there are confusions out there.
One last thing.
Okay.
So now, the case of, I guess you had 6 quarks, right?
Yeah.
Wrote down.
Well, it's 3 4 anti-quark.
3 quarks, then you wrote down your, the little basis there, and then you took the generic case where all the coordinates are different, right?
Yeah.
You got a big mixture.
Yeah.
And then what is your argument that, okay, if you make some of these the same, then you recover the same things involved in all the same diagrams involved in calculating 2-point
Yeah.
the hierarchy for a 2.
Yeah.
So that's what I'm talking about.
Yeah, right. The hierarchies, the hierarchies for 2 points or for 4-point functions are contained right in the bigger things. Right? To a certain level. So looking at the more complicated thing, so by coincidence limits, if you have solved this, you have solved the other as a special case.
So, now somehow it doesn't seem like as intractable as you might first say.
Well,
You're not looking for the whole. You're not looking for the whole.
Well, no, the problem is still there. Let me try and go back. Where is my big box? Here is my big box. If I look at the things that I have down here, so if I look at the evolution equation, the top left corner it's the derivative of the top left corner. Contains the stuff at the bottom right, bottom right box. But now I would need to solve the equation for the bottom right box. And that is in a box that is not shown, because then I have to take 4 cubical pairs and do the same thing.
Yeah, but now you don't have to think about them as having being all independent, right? Because you want them.
Well, if I no, once I have once I have written my parameterization in terms of say 4-point functions, then I don't need the rest. Then this is enough. If I want to go to 5-point correlations or 6-point correlations, then I need more of those. But for 4-point correlations, this is all I need.
Parameterization.
Yeah, right. In this sense, it throws away the influence of genuine 5 and 6 points and higher endpoint correlation. But since these are, I mean, what you would normally expect that these become flimsier and flimsier, like the signal is tinier and tinier, and this is a reasonable function to start from. But to build up correlations, you need more gluons connecting the bits and pieces of a diagram. Right? So naturally, this is higher order information. It builds up there. That's the idea of truncation. And the little miracle is that we can do it in negation. That's a little miracle, because this is not something that we can do for arbitrary reasons. But Wilson-like correlates. Okay. More questions, sir? Then we should stop recording. Thanks, guys, again.